Okay, Professor Walraven, your computer is dark.
Yes. Yes, Dan. And Vanderlei. Of course, he's busy. He's just walked out. It's hard to express how delighted I am to be here today at this very special occasion. Because I know Dan Kleppner for a very long time, almost embarrassing long, since the 70s, mid-70s. And we have been competing. But I can tell you one thing. If you need a competitor, and you like him to be a gentleman, choose Dan Kleppner. And it has been a joy to work in the same field. And I thought, what to do on a day like this? Maybe reflect some of these old things. I should admit that it has been a long time since I looked at them, but nevertheless, it's interesting. I started in the field of ultra-cold gases when I was a master's student. Then we had a visitor. His name was Dick Etters. He was a professor of theoretical physics from Fort Collins, Colorado. And he was visiting us, and he was working on the properties of possibly making metallic hydrogen. But in the context of that, there was also a project going on making rocket fuel. It was trapped atomic hydrogen in some molecular matrix. It was thought there was big money available, both in the West and the East, to make rocket fuel. It started with an application. And I learned there something about theory, because Dick Etters was the first person that convinced us that atomic hydrogen would be a gas. And would never be able to get it into some kind of solid state, except at exceptionally high pressures. For doing this beautiful work, the projects that were based on it were cancelled, and he lost his grant. And he saved probably so much money as a theoretician to be wasted on a project that will never work, that he could easily reach his final days doing theory for the cost that he saved. But he lost his grant. So it meant that I met some aspect of theory that can be surprising. At that day we started to work on atomic hydrogen. I was the only graduate student. And you cannot imagine how delighted I was when I found out that across the ocean there was at least one other graduate student working on this topic. Because it became rapidly clear that more than one graduate student would be appropriate for a problem of this type. And so that's what I would like to say as an introduction. But there's much more. Of course, if you look here, this is ICAP in 1969 in Amsterdam. 1969, an important year. Yeah. Oh, 96, yeah. And you see here the distinguished speaker, and you can imagine what topic he was talking about at that conference in that year. And if you look, you can see many. I show this because, of course, if we think of Dan Kleppner, we immediately also think of his enormous contributions with regard to the ICAP conferences. And of course, Dan is in the audience. There you see him. Yes. Yeah, here. Ted Henge, Christophe Salomon in his neighborhood, and many other well-known people in the audience. I was looking for a photograph, and I found this one. This is Dan Kleppner. What I like about this photograph, it's very characteristic. And what I like about this photograph, that if we look, he didn't change a bit since 1969. In 1969, where were we in 1969? We were filling up the work of Pepijn Pinkse, the thesis of Pepijn Pinkse. And we were working with atomic hydrogen. Of course, 1996 is after 1995. You should know that. And what you see here is a plot. Here you have a Joule-Pritchard trap. Here you see a plot of the magnetic field. Here you have high field, there you have low field. Here we have a low temperature dissociator. We had all walls covered with liquid helium. There was a window in the bottom and a window on the top, and we could measure this sample by sending a beam of Lyman alpha from the bottom of the cryostat up to the detector that was mounted on top of the cryostat. And if we were striking the dissociator, then we would produce high field seeking atoms and low field seeking atoms, and the low field seeking atoms were collecting here, and our task was to find out why this system did not boson condense at the time. Of course, it's after 95. So in 95, of course, there was an incredible achievement in the sense that BEC was achieved, and we know very well who started a wave of activity. A field that started with a single atom where possibly you get Bose-Einstein condensation was replaced by a situation where it was up to the imagination of the experimentalist that any system could be Bose-Einstein condensed. So, but if any system could be Bose-Einstein condensed, why didn't hydrogen Bose-Einstein condense? Why did it take so long? Let me show this. It started 10 years before that. And Michel already showed this slide. It was an idea of Harold Hess, and it's called evaporative cooling. If you have collisions between the atoms and you want to go to the Boltzmann tail, then you need many collisions. And you let the hottest atoms disappear, and that gives you cooling. So some atoms cool, some atoms heat, and the evaporative cooling goes proportional to the density, velocity, collisional cross-section, times an exponent that gives you the probability to escape. Very simple method, and we all used it. We all use it today very efficiently. It works like a dream. The first trapping was done at MIT in a group of Dan Kleppner and Tom Graytek. And here you see the arrangement that was done. And the atoms escaping from this region could be detected by a microwave system. In Amsterdam, we were having a similar system. Here you see it's all in the cryostat. Here you see a dilution refrigerator. So hydrogen is the only system where you can load the trap without using optical methods. And that was used. Because you know the first atom, neutral atom that was trapped by Bill Phillips in '85. And the second neutral atoms that were trapped were the atoms at MIT, the hydrogen atoms. Okay. These the difference between the experiments that at MIT they immediately tried to observe the evaporative cooling and see the cooling. But that was difficult because there were no proper thermometry. You had to do a lot of modeling. So we thought rather than having the evaporative cooling work, close the system at the end so that you always get thermal equilibrium, by thermal equilibrium with the helium surfaces surrounding the gas. And then at least you know what the temperature is, and then you can see whether the properties of the gas is exactly what you expect. That was the difference in approach. And I recall with Dan and Tom Graytek that there was always differences in approaches which were complementary. So it didn't work. So things had to be calculated. Well, these, of course, there are only 4 hyperfine levels, but this is all the spin relaxation you can have between hydrogen atoms. They were all done. That part was done, that we understood exactly what it does. A paper that influenced a lot of people, but also us in Amsterdam, was the paper in which Wanderlei was involved. And it's a paper by Bagnato, Pritchard, and then Kleppner, in which a simple model potential was introduced. It's a very simple model potential, but it was of big importance because it enabled us to do rapid modeling of the system and explore situations. And that was a model that was very much used in developing the theory of evaporative cooling further later years. Of course, we had to detect the sample. We couldn't take a snapshot, but we did it by spectroscopy. And here you see the Lyman alpha lines for sigma plus and sigma minus polarized light. And then your sample looks quite different. You might think that the pi line would be of the same position, but it is not, because massive Faraday rotation in the sample. These things were all being investigated, and you can see that through the spectroscopy, you really had to know your optics very well in order to interpret the data. Another theoretical effort that was done in order to understand why it didn't Bose condense was an effort together with Yuri Kagan and George Slapnikov. At the time, it was not a very popular paper because it was a so-called bad news paper. Yes. Bill is smiling. You will recall this paper. Yes, it was a bad news paper because here's the density versus temperature, and and this is the evaporative cooling line. And once you would like to shoot into the BEC like we usually do, theory, and that was professional theory with proper mean fields, calculating the whole thermal exchange between condensate and system, made that you could not get more than a few percent of condensate. And rapidly you lose your sample. And why was that? Of course, it's now known as the ratio of good to bad collisions. If we teach the students what happens if you take a square well and you make the well deeper, then the scattering length of 2 colliding items go through resonances. Once you get a first bound state, second bound state, third bound state. And, well, you see there's lots of choice. But what happens to be the case in the case of hydrogen, the scattering length is really anomalously small. So small that it's of the order of a Bohr radius. Very anomalously small. It's there. It's 1.22 A naught. And because A naught, because the chemical potential is proportional to A, it means that the chemical potential is very small, and the width of a condensate, the condensate broadening is very weak, and that means you get the density shoots up and you lose your sample by 3-body recombination. Well, maybe you're familiar to the fact, I see there's also many students in the audience, which is great. But maybe you're familiar with the fact that if you have a positive scattering length, then you have at least one bound state. Hydrogen has a positive scattering length, but no bound state. And it's plus 1.2 A naught. So in fact, this curve goes up and goes positive and goes to 0 because the hydrogen potential is not a square well. I think this is the only exception to the rule. Yeah, so if it's 0, now we would say you would choose a Feshbach resonance. You apply a field and you can make one of the levels resonant with a rotational vibrational state. Well, actually, in 1981, when we were starting our experiments, we hit the first Feshbach resonance. But it wasn't called a Feshbach resonance. At the time, we called it, and it was done by the people who explained it, it was a group of Walter Hardy, inverse predissociation. And the chemist knows what it is. The chemist knows that if you are in the V equal 40 J equal 4 state, and you're resonant with one in the singlet potential, you will resonant with one of the branches of the triplet potential, then you can dissociate through a difficult process because you go from J equals 4 to an S-wave state. Or if you go in the other way, I should say, you go from the S-wave, try to couple to the G equals 4. That's what we now call a G-wave resonance. It was explained, but as you can see, it only works for the curve which runs down, which are the high field seeking atoms that were the atoms that were used initially. And for the low field seeking atoms, there's no Feshbach resonance in hydrogen. So that path was closed. And that it was there was observed. Here you see all the groups that worked, including MIT. Here you see an effective loss constant versus 1 over T. And it has a characteristic behavior which has to do with the role of the helium surfaces, which is not too relevant for this discussion. But where the theory would say you go here, the data turned around earlier, and that was due to the presence of the resonance. So already in 81 there was a Feshbach resonance, but it was not recognized, and it was in a bosonic system, and and we know that in bosonic system you lose them very fast, your atoms. You need fermions to do that. Okay. So in order to establish where we were, we did the evaporative cooling in '96. We did it in our system. And, but there was an aspect that was not taken into account because the theory of Vanderlei and later what we did ourselves was presuming ergodicity of the system. You had to do a Boltzmann equation, and you presumed ergodicity in the system. But there was a problem in our case. That means that the atoms have to escape. In fact, they have to escape. If they escape to the high field, and they have to go along the length of the sample. And it means you go like this up, and you meet the particles in the center of the trap many times. And it means, whereas in order to reach the tail of the Boltzmann distribution, you need many events, to go back, you only need 1 of 2 collisions. So what happens, and that was worked out in detail in the theory paper with George Slapnikov, is that you get back. And that means that the evaporation along this direction is not the 3-dimensional evaporation where you presume that if you have sufficient energy, your particles immediately escape. No, you have to look at the probability that the dynamics of the particle will really bring it to the evaporation point, to remove it from the sample before it has its chance of colliding. We did the measurements. And there you see, this is here we changed the trap depth. Here you see the 3D model, here you see the 1D model. In our case it was 1D evaporation, and all our experiments were based on the 3D situation. Here you see also the BC line, 3D evaporation, 1D evaporation. Then we knew immediately what had to be done. You need to do RF evaporation. In fact, we knew that much longer already, from the beginning of the 90s, but we tried to optimize the situation by different profiles, and you can see that you could optimize the evaporation curve, but quite tantalizing. Just before entering the BEC, it didn't reach it, and it was all due to the 1-dimensional evaporation. All these things being known, I switched to the heavy metals, to the alkalis, and as we all know, Dan Clapton and his group continued. And a few years later, in '98, they did a wonderful experiment where they achieved BEC. And here you can see what they measured. They came in like this, and then when they reached the BEC line, the sample declined like this, exactly as the theory had predicted. So it was not bad news. It was not a bad newspaper. It was a bad newspaper for hydrogen. And I was discussing this point with Wolfgang Ketterle, and he was aware of this, that in the alkalis this difficulty would not exist. Okay. How much time do I have? $15 minutes? Okay. Okay. So this is also the way it was observed with the BC peak that Michel Duc also showed. It's a beautiful result, and we were delighted to see it because, of course, it was a 20 years effort, and it was great to see that hydrogen indeed could be Bose condensed. Okay. I switched. I would now tell something I worked on recently, an idea about things you can do with the alkalis. And this was an idea that's probably presently put into experiment by, worked out together with Jesper Levinson and Dmitry Petrov. It's about mediated interactions. Near these Feshbach resonances that have been studied intensively, there are universal states, free-body states, Efimov states. And this paper is about another type of free-body state, which is a non-Efimov state. It's the interaction between potassium-40 and lithium-6. We have a certain binding energy, which is inversely proportional to the scattering length, the square roots. If you are almost bound, then you have these asymptotic bound states, where the most of the probabilities, the halo states, most of the probability of the wave functions are in the classically non-accessible areas. And that means for both the singlet and the triplet potential in the alkalis, here you have the triplet and this is the singlet, you get the same long-range behavior. And it's this behavior that just depends on the binding energy. So it's the short-range models that have been used in the early days of nuclear physics. Okay, how do the mediated interaction work? We have two potassium-40 and a lithium-6. And now we look at the exchange between the two potential wells of the two atoms. And it means you get a linear combination of these two. If you calculate the binding energy of this system for these weakly bound states, then you find that the binding energy, that the kappa, so the square root of the binding energy, scales inversely proportional to R. And it means that the effective well depth depends inversely proportional to 1 over R squared, the distance between the two potassium atoms. So if you now add rotation to the molecule, then you get this effective potential plus a rotational barrier. And you can add it up. It gives you this 1 over R squared dependence, which turns out to depend on the end-over-end rotation of the system and the mass ratio of the two atoms. Okay. So if you now take this potential, and you start to vary the mass ratio, then what you can see is that you can, for L equals 1, so for the P waves, you can go from a repulsive situation to a situation with a minimum, or to the limit where you have what we call the Efimov limit, where you have the formation of the traditional Efimov states. Now you see it is a repulsive barrier, so what you can do is tunnel through the barrier and go into this potential well. So in our case, the mass ratio is 6.7, so we are in this situation, and it means you cannot form these bound states. The binding energy is not, the molecule is not bound, and it means that you only have a p-wave resonance in this system. So how can you do this with atoms and try to persuade them to anyhow show this universal trimer state? The idea is the following: we bind by confinement. What happens if you go from 3D to a mixed dimensional situation where you have two in the plane and the lithium, the light atom that is doing the exchange, is in 3D? Then the end rotation of the molecule is no longer L times L plus 1 for its rotational barrier, but it goes like L square. That means that the rotational barrier is less in that case, which lowers the potential energy and can create the bound state. So this is the idea that we are working on. And I understand from the group of Rudy Grimm that they are presently having their first results on this on the P waves. So the idea is bind by confinement, and for our case, this is the ratio of the scattering length over the confinement length, and for potassium lithium, we have the red line, and that means that we can find the ratio of scattering length to confinement length such that we get the bound trimer state, and rather than the p-wave resonance. Rudy Grimm is now working and measuring the p-wave resonance. So it almost has become unnoticed, the enormous progress that we have made since the very early days of the experiments with atomic hydrogen. And it's absolutely delighted that you can now design your experiments to do sophisticated three-molecule physics, as in this particular example. And there are many theoreticians who are also interested to incorporate these three-body interactions in many body systems. This is where I would like to stop. I thank you for your attention, and I would like to thank Dan for being such a great example in the scientific world.
Yeah, I was interested in how the three-body recombination is affected in this P-wave resonance.
There's some conflicting theory there. Yeah. So, on those moments, I feel like an experimentalist. You should measure, because it is really something you can do. But yeah, well, the idea is that there's a real possibility that it would work, but there's some remarks on the model, because this is an extremely simplified description of the three-body model. In fact, you have to do the real three-body problem, but this is only a presentation to emphasize the physics of it rather than the sophistication of the theory.
You mentioned the difficulty of 1D evaporation as being one of the stumbling blocks. Of course, you also mentioned the good to bad collision ratio, which is also a bad thing in hydrogen. But what I'm thinking about is that in the early days of atomic gas BEC, a lot of people worried about lower dimensional evaporation as well. For example, because of gravitational sag in magnetic traps, this would change the dimensionality of the evaporation, and a lot of people worried about that sort of thing too. Today, you hardly hear anybody talk about the dimensionality of evaporation. You just evaporate and you get a BEC and you go on and do other things. So,
No.
so I was wondering about your perspective about this.
Yeah, well, it means you take another atom. Or, and that's what often done, people take a Feshbach resonance to make the scattering length such that you can do the evaporation in 3D. Moreover, in our case, we were confined and we had to evaporate over the barrier. In a gas cell where you have your sample in free vacuum, you can escape in all directions, also in radial direction. So that's also a difference.
Well, but what I'm thinking about is that it seems like the idea that you have gravitational sag and that changes the dimensionality of the evaporation doesn't seem to be very much of an issue today.
It becomes an issue
well,
when you choose your scattering length very small.
Sure, certainly if your scattering length is small, you're doomed in all sorts of ways. Yeah. No. So my question was not so much about hydrogen. I think that, it was funny. We always thought that hydrogen was the best thing there was, and it is for almost everything but Bose-Einstein condensation. But my question has more to do with the atoms that are the favorites today, which, generally, although not universally, have reasonably large scattering lengths. And when they don't, as you say, sometimes use a Feshbach resonance to fix that. Things like rubidium-85, which has all kinds of funny difficulties you fix by clever tricks. But just your ordinary garden variety rubidium-87, sodium-23, even cesium, which has a number of difficulties. People worried about the dimensionality of evaporation early on, and now it seems that has disappeared from the concerns. And I'm just wondering if you had some comments on that.
No. You say why in cesium you would eventually, if you would use this at very low temperature, you would eventually also run into such a limit.
Yeah, well, cesium had these problems with the fact that there were Feshbach resonances near zero field.
Well, there's
so
many other things in cesium. But
and that it was hard for the atoms to get out because the scattering lengths were so large and the atoms couldn't get out of the gas.
Yeah, but you probably can cool a long way before you are in the very end. You start to be facing the 1D effect, and once you enter the BC, you don't worry anymore.
Exactly.
But in our case, there was no way of escaping except along the very end.
Yeah, no, that's right. That was a difficulty
but
for
it's
sure.
Probably that you don't have to do the full trajectory of the evaporative cooling with the handicap of the 1D if you have these heavy atoms.